In this lecture, we are going to look at Epsilon greedy in code. I want to remind you that if you haven't yet done the previous exercises, you should not watch this lecture until you do. You will get most out of this only if you have attempted to code this yourself already. With that being said, let's begin. So after some basic imports, we're going to initialize a few constants. We set the number of trials to 10,000, we set epsilon to 0.1, and we set the probabilities for each bandit at 0.2, 0.5, and 0.75. These are the win rates for each bandit. Next, we create the bandit class. Inside the constructor, we take one argument p and we set three instance variables. Self.p represents the true win rate for this bandit. P_estimate represents the current estimated win rate, and self.n represents the number of samples collected so far. Initializing p_estimate to 0 ensures that the rest of our calculations are correct. Next, we have the poll method, which returns a 1 with probability p. As you recall, true is equivalent to 1 in Python, so returning a boolean is also okay. Next, we have the update function, which updates our current estimate of this bandit's mean. Inside this function, we accept a value for x, which can be 0 or 1. We start by incrementing n, since we've just collected one more sample. Finally, we update p_estimate using the formula we derived in the earlier lectures. Next, we have the experiment function. Inside this function, we initialize our bandit objects with their respective probabilities. Next, we initialize a rewards array that stores all the rewards we collect at each trial. Next, we collect a variable for the number of times we explored, the number of times we exploited, and the number of times we chose the optimal bandit. Next, we retrieve optimal j, which is the index corresponding to the bandit with the maximum true mean. Remember that in real life, you wouldn't know this information, but since this is a simulation, we do. Next, we do a for loop, num trials times. Inside this loop, we implement our epsilon greedy strategy. We start by drawing a uniform random number and checking whether or not it's less than p. If it is, we choose a bandit at random, and we increment the counter for the number of times we explored. Otherwise, we choose the current best bandit based on our estimate of p, and we increment the counter for the number of times we exploited. Remember that we can't use the true p in our algorithm, since in real life we wouldn't know this value. Next, we check whether or not j is equal to optimal j, and if it is, we increment our counter for the number of times we selected the optimal bandit. Next, we pull the jth bandit arm by calling the pull function. We get back a reward x. Next, we assign x to our rewards array at the index I. Finally, we call update on bandit j so it can update its estimate of the mean reward. Once we've completed this loop, our experiment is complete. The next few steps just provide information to us about how the experiment went. So first, we print out the mean estimate for each bandit. You should find that these will be pretty close to their true means most of the time. Next, we print the total reward earned, the overall win rate, the number of times we explored, the number of times we exploited, and the number of times we selected the optimal bandit. Next, we plot the cumulative win rate over time. To do this, we start by creating an array to represent the cumulative sum of rewards. In order to convert this into a win rate, we need to divide each cumulative sum by the total number of trials done at each index. So we need to divide the first element by 1, the second element by 2, and so forth. We can accomplish that by creating an array of length num trials and adding 1, since counting in Python starts at 0. If we then do an element-wise division between the cumulative sum of rewards and this A-range array, we will get the cumulative win rate per iteration. Our hope is that this approaches the maximum win rate, minus any penalty for selecting suboptimal bandits due to non-zero epsilon. We also want to plot a horizontal line at the maximum win rate to show what value our cumulative win rate is trying to achieve. Alright, so that's it for this function. Let's run this and see what we get. Okay, so first let's recognize that the optimal bandit is chosen correctly. It's the bandit at index 2. Next, we see that the estimated means are quite close to the true means. Recall that these are 0.2, 0.5, and 0.75. We see that the total reward is 7,255, which is close to the expected reward of 7,500 if we had selected the optimal bandit each time. Of course, we didn't, so that's why our reward is lower. We see that the ratio of exploration to exploitation is approximately 1 to 9, as expected. Finally, we see that the number of times we selected the optimal bandit is slightly higher than 9,000, since we are still allowed to select the optimal bandit when selecting randomly. And if we look at the cumulative win rate per iteration, we can see that although it increases and converges over time, it does not approach the maximum theoretical win rate. As a final exercise for this lecture, here's how you can extend what you've learned. Instead of using a constant epsilon, which always yields a suboptimal average reward, you should instead implement one of the decaying epsilon strategies we discussed in the theory lecture. In the long run, you should see that this eventually leads to exploiting the true optimal bandit.